This work was done over the past roughly 10 years or so I'll present also some experiments that were not done by myself, and we will see as we proceed. So first of all, the concept weak ergodicity breaking came from Jean-Philippe Bouchot in the context of analysis of experiments on glassy systems. These were macroscopical data that the magnetization in spin glasses show some correlation functions which were non-stationary. And he understood that this must lead to some very special form of ergodicity breaking, which he called weak ergodicity breaking. And our goal is to understand what does this word mean. My starting point here was from dynamics of single molecules. And this will be also the starting point of these talks. I will present at the beginning, some experiments on single molecule dynamics. This will include blinking quantum dots. And this will include diffusion of molecules in the cell. And then from that, later on, I'll go to build a framework, a stochastic and framework which describes time averages in this system. And towards the end, I'll go back to the original model considered by Jean-Philippe, which is the quenched trap model. So at the beginning, it will be mainly motivation. So first of all, let us define what exactly do I mean by ergodicity. So I really mean it in a very simple form. So let us consider a particle in a heat bath, and the heat bath is with temperature T. Here you have some spring, so it's one particle. And this particle has a trajectory. It's fluctuating around the minima of this force, around its equilibrium. And then what we can do in the laboratory, for example, well, we can take a time average. Of course, in the laboratory, it will not be for infinite time, but we can imagine an infinite time. So we can define a time average of this stochastic process, which I'll denote by an overbar. On the other hand, we can also construct an ensemble, both in theory and in an experiment. We can take many copies of this physical system and construct an ensemble and look at the position at some given time. And then you can measure, for example, the distribution. And because we are dealing here with a simple spring, and we are dealing with a canonical setting, you'll get here a Gaussian distribution according to Gibbs statistics. And then you can perform the ensemble average, which will be denoted by these brackets over the equilibrium probability density. And the two answers, the time average and the ensemble average, will give the same result. This is, of course, related to other concepts of ergodicity, like equal probability of occupying the shell in the microcanonical setting, etc. A slightly different type of equilibrium is what I also want to discuss, maybe less known, is that we can define a notion of ergodicity also for observables outside of equilibrium. And this is, in fact, done a lot in the laboratory. And for this, consider, for example, you have a microscope and you follow the trajectory of a single Brownian particle in liquid. The experimentalist wants to estimate from this time trace, he wants to estimate the diffusion constant of this particle. What does he do? He does a time average. And this time average, which I'll denote again by overbar as time average, this is delta squared. You take the increments, you take the position of the Brownian particle or whatever it is, at xt prime plus delta minus xt, and you square it. So while the Brownian motion is not a stationary process, the increments are. And you see here I average over time and divide by time. And t here is the measurement time, delta is the lag time. And when this measurement time is going to be big, and if you have a long trajectory of a Brownian particle, then in the limit, this time average will go into, in one dimension, 2 times d times delta, the lag time. And of course, you can do another experiment. You can measure many Brownian particles together, and you can measure the ensemble average. And that will give you exactly the same diffusion, diffusion coefficient for as you did for one long trajectory. Again, that is valid for Brownian motion, but if you look at, let's say, diffusion in disordered material, this is going to be my talk, it will be absolutely not valid. For example, consider a random walk in a disordered system. The two time average and ensemble average will be totally different, as I will show later in the talk. So to start the discussion, let us consider, first of all, I want to discuss so-called blinking quantum dots. For that, I need to do a detour, slight detour into some very basic things that you know, I hope, from graduate studies on how do single molecules fluoresce. So let us start with one typical picture, which is, later I'll call this ergodic. But consider you have a molecule, for example, some organic molecule on a matrix. It has a singlet ground state, and it has some singlet excited state. And what you do is you take your system and you excite it to the excited state, then it relaxes, and then vibrational relaxation, then it emits a photon, it goes up, emits a photon, goes up, emits a photon, and you are observing the photons, the fluorescence that is coming out. Once in a while, this system may have, for example, a triplet state. And this triplet state might have a long lifetime, let's say 10 to the minus 3 seconds, compared to the fluorescence lifetime, which is roughly 10 to the minus 9 seconds. Now, let us imagine what will you see when you observe such a molecule, one molecule at a time. This is well known in optics from more than 20 or 30 years ago. What will you see? You will see, so this is the fluorescence coming out. Again, the laser field is a continuous wave. So you see some photons coming out, then a dark state, photons coming out, a dark state. So again, you go up and down emitting photons, then you just rest here, etc. So a usual standard way to analyze this, you define a cutoff here, and you define on times, and you define off times. And if you believe ordinary quantum mechanics, you can calculate the transition times by Fermi-Golden rule, etc. These times should be exponential. And this exactly is what measured here. You have an exponential off and on time distribution, so you have intermittency. But it's totally ordinary, and this will be ergodic because characteristic time scales exist here. Now, I would say that many people investigated this blinking. Why? Because let's say you have a system and you have one molecule emitting. How do you know it is a one molecule? How do you know you observed one molecule in a system or one quantum dot? You know it because it blinks like this, right? So this was used as a proof that you are actually looking at one molecule at a time. What will happen if you look at many at a time? You will see just a plateau of fluorescence because you will not be able to see the blinking at all. So then roughly 15 years ago, people were starting doing similar experiments, but they do it on quantum dots. And these are going to be weakly non-ergodic. In the following sense, what is the quantum dot? It is it's, roughly speaking, it is a semiconductor, but very small. It's roughly 2 nanometers. For example, cadmium selenide. It has some surrounding. There are different types of quantum dots. For example, quantum dots that are surrounded by polymers, or quantum dots with a core and a shell. So roughly speaking, these are a particle in a box, but not a box, but in a sphere. And measurements of this were done maybe for 40 years when people have looked at ensembles, many. This is done like this. And you can change the size of the quantum dot, and then you can see quantization of energy levels like everyone here knows from particle in a box. The energy levels are quantized. You change the size of the quantum dot, you control the energy levels as you expect. The surprise came much later, maybe, well, it's already pretty long already, but 15 years ago, when people have observed one quantum dot at, let's say, very low temperature on a matrix. So again, you are exciting it with a laser field, and this is the intensity. So you have your bins, and 100 bins that, let's say, in 1 millisecond or something like that, you have 10, you record 100 photons. So this is the current of photons coming out from this blinking quantum dot as a function of time. And the first thing you do when you see this, you say, okay, this is similar to the single molecule blinking, but I want to claim it's very different. And you, first of all, you need to ask, why do you have this blinking of this quantum dot? The answer was given by F. Ross. This transition from an on state to an off state, on-off, is believed to be due to the fact that this quantum dot is charged and discharged, charged and discharged. So what you are seeing here, this transition between on and off, is the simplest chemical reaction of charging, non-charging, charging, non-charging. This is related to the fact that when the quantum dot is charged, the charge quenches the light. So you see it as off. This is based on something called Auger process from condensed matter physics. I'm not going to go into this. I'm going to discuss only the weakly non-ergodic properties. And this you can, roughly speaking, see with your eyes. First of all, as usual, we can define some threshold here, and you can define on times and you define off times. And if you look carefully, so you see here there's a short off time. This is becoming bigger, bigger, bigger. This is even bigger. Maybe this guy's even bigger. This guy's even bigger than this guy. So you see with your eye nearly, and soon we'll analyze this, that there are many scales of time here, from very short to very long, and this is indication for scale-free dynamics. And then, of course, you can do all kinds of things with this time trace. You can take a correlation function. You could take the power spectrum. You can take the time average intensity, which will give you the number of photons. And you can expect, maybe it will converge. The answer is no, it will not converge. So these blinking quantum dots also give you the so-called 1/f noise. And the point is that if you average once, you get 1/f. But then if you average one other time, this is another trace. So you see that the amplitudes of the 1/f spectrum, they vary from one trajectory to the other. They are not the same. They are not reproducible. Ergodic behavior would be that all of them in the long time limit will fall on the same line, but they are clearly fluctuate. And this is not only a property of the 1/f noise. This is a property of any observable that you perform a time average. It will be this. It will not be reproducible at all. And this, in that sense, this nano system is exhibiting some kind of ergodicity breaking. We discussed this a lot on the 1/f noise. I don't want to go into this direction now. But I would like just to explain in an intuitive way, why do you have here ergodicity breaking from the phenomenological point of view? One looks at the probability density function of the on and off times, and these in the laboratory, they fall off like a power law. We had Flach last week talk about this type of intermittency with power laws. Here you see them in a laboratory. They are, however, very different than what Sergey was talking about. These are distributions of on and off times which decay like a power law, but the exponent here, which I'll call later alpha, is less than 1. For example, in this experiment, it's half, roughly half. And this means that the average time you spend in these on and off times is infinite. Because if I take tau and I multiply by this guy and I integrate, then I'll get infinity. Of course, in any finite time experiment, the biggest on and off time is always less than the experimental time. What I mean by infinite waiting times is if this curve will continue to infinity, the average would be approaching infinity. Now, once you have a divergence of a time scale, this is indicative of some ergodicity breaking. This is obvious, because if the microscopical time scale in your dynamics is diverging, then obviously you cannot average for long enough time in order to see convergence to ergodicity, because ergodicity always means that the time scale of your measurement is much bigger than the time scale of your dynamics, always. Why do we call it weak ergodicity breaking, though? This again, following Bouchot. So Bouchot had this general vision in the context of a trap model of glass, and he thought of ergodicity, roughly speaking, in two ways. You can have something which we will call strong ergodicity breaking, and that is you have a system and it is decomposable into some subunits. And then let's say you start here, then you remain here forever. That is scenario one. It's very common. It exists many, many cases. One can then discuss about ergodicity within a sector, so to say. This is one option. Maybe there are many others. But a second option is that you have some sampling of your phase space. So every kind of subunit is connected, maybe directly or indirectly, with other subunits. But the waiting times in each of these subsectors is a power law, and the infinite sojourn times means that the time average will not be equal to the ensemble average. And why did he call it weak? Because here you have sampling of your phase space. Here you do not. And in that sense, it's a weak ergodicity breaking. For example, for the blinking quantum dots, we have only two states, on and off, but the number of visits in the on state and the off state can be thousands, and you jump between them many times. So you are sampling the two states many times. What would be strong ergodicity breaking in this context of this type of experiment, let's assume you start in the on state, you remain there forever. That's what we call strong. Or you start in the off state, you remain there forever. But of course, the experiment shows you, no, you remain like this. They could be different, but what is important, they could be different, but important that some of them have power law distributions with a diverging mean. And for example, I should mention, because this was discussed last week, in Hamiltonian systems, I do not think this will happen for finite systems. So these are complex systems, like glassy systems, out of equilibrium, because of what Sergey mentioned of Katz's theorem, that you have a finite return times. And we had previous week examples of power law distributions, but always the alpha was always bigger than 1. But so it's not Hamiltonian dynamics the way I see it right now, unless someone will prove otherwise. But you can have only, yes, you can have only also one, but the results will be very different. An example of one is the Pomoma-Neville map, where you have one unstable fixed point, and you work in the so-called when the Lyapunov exponent is 0. Then you can build a generalization of the Pomoma-Neville map with 2 unstable fixed points, and then you'll have 2. So what? It is coupled to its surrounding, and with the laser, what is happening, what we believe, again, following efforts, is when you excite it with the laser field, you go to the excited state with the electron can jump outside of the quantum dot, and then it does maybe some diffusion outside, and people are battling what exactly is this diffusion, is it normal, anomalous, etc. Many models, no conclusions. And then it comes back, and this turns on and off, but essentially the system is really not bounded because of the environment. Okay, I would say that on the quantum dots there are maybe hundreds of experiments, because everyone is trying to get rid of this non-ergodicity. And soon you'll see why. This is very important. People have tried to get rid of the blinking for 10 or 15 years, but with no success, for many different systems. So I think only condition is that the environment has to be disordered. I think that is correct. So now the point before I go to theoretical part is more motivation is I want to say that these power law waiting times are common, and in fact these are known from the 70s. These are not a new invention. These were found, the oldest work I know is Sharon Montrol, 1975. It was about diffusion of electrons in disordered materials. But today the difference is that in the past people were discussing this with ensemble averages. Now we are talking about single molecule trajectories, and we are doing time averages. That's the only difference. But I'll give you one example, but there are many. So this is an experiment done by David White, and he has here actin network. Actin network is important in biology. And you have here this spaghetti. It's all in water at room temperature. And you have a bead. The bead is roughly of 1 micron, and you have a scale of this mesh. And then you do a diffusion process. So this is a diffusion in a disordered material, and I plotted here this dot. This guy is so small, it will just diffuse in water. Its diffusion is normal. But when your size of the bead is of order of this size, you get a lot of sticking and jumping in this thing. And then you can follow it in an experiment, and then you can see some particles are localized, and for many hundreds of seconds, and other particles are jumping. So if you want, this is like Anderson's problem, but in high temperature, right? There's no quantum mechanics here. But the system is disordered, and then you have these waiting times in different, so this is position, let's say, along the x, and this is time, and you get these sticking times. And then you can analyze the distribution of these sticking times. And again, this is the probability density function of these times. It follows more or less a power law distribution. And here in this case, this alpha will depend on the size of the bead. You can change the size of the bead, and you can change alpha. This was done in this experiment. And it was known long time ago that if you have these long-tailed waiting times, then the mean square displacement of many particles, an ensemble of particles, and if alpha is less than 1, will grow like t to the alpha, because the number of jumps is not proportional to time, but it is proportional to t to the power alpha. Again, an example of average waiting time is infinite. There are very important experiments in the cell, and here there are hundreds of experiments. So for example, this is an E. coli cell, and this is one molecule, which is the messenger RNA. Its job is to move information from the DNA outside of the cell. And then you follow this messenger RNA in this cigar-like cell. So here the boundary is important. And you see, roughly speaking, it's covering the full phase space. So you explore phase space. And you see here by the positions, you see here more or less full exploration. Maybe here there's some object that you didn't see it, but you see the shape of the system. And then you have these trajectories. And then, again, in many laboratories, you look at the time average, but now you are looking for diffusion, like I showed before. And this is the time average diffusion mean square displacement. So what do you see? There are two experiments here, actually. Here, it's done in water. So here you see that, first of all, diffusion is normal. Secondly, when you repeat the experiment in water, each time you get more or less the same result. That is the ergodicity. But if you put the molecule in the cell, then each time average gives you a different result. There is a distribution, so to say, of the diffusion constants. And there is no ergodicity, or maybe more correctly, maybe we don't know if here it's a bit subtle, because the question is this ergodicity breaking, or is it the fact that different cells are different is very difficult to answer. But at least from observational point of view, the time averages are totally random, and you can quantify the distribution of this guy. This will tell you how many guys are fast, how many guys are slow, and this is important for biology if you want to quantify how fast information is moving in the cell. By the way, in these experiments, these are related to the first experiment on blinking quantum dots. The dream at the beginning of this single molecule era was, let us take a single quantum dot, put it on a messenger RNA, for example, and then follow it. That would be great. Then we could, understand biological processes in the cell. But because of the ergodicity breaking, this is impossible, because this blinking quantum dot turns off for huge amounts of times. So the problem of ergodicity breaking is important. So what you do here is actually you put on the messenger RNA, you put several blinking objects, and then you see them all the time. But that's bad. Why is it bad? Because then you are modifying the behavior of the messenger RNA. So hundreds of laboratories are trying to get rid of the blinking, are trying to follow single molecules in the cell to understand the processes that make life possible. So now I want to discuss a general theoretical framework which describes and quantifies how big is the ergodicity breaking, and what exactly do I mean when I say weak ergodicity breaking. And here I'm following this continuous time random walk, which is a stochastic process. It's a renewal type of random walk on the lattice. This is my lattice. You have jumps, let's say, only to nearest neighbors, with some probability to jump to the left and some probability to jump to the right, qx and 1 minus qx. And we are assuming now that all cells are the same, in the sense that the waiting time PDF has a power law distribution, but with alpha less than 1, in such a way that the mean waiting time is finite. So again, for blinking quantum dots, these will be 2 states. For the diffusion and active network, you might have many states like this, etc. And the question is on time averages. So in time average, an important quantity is the occupation fraction, which is the total time you occupy one cell. So I move left and right many times in this room, and I measure how long do I stay here in the total measurement time, and that is Tx over T. This is important because essentially in ergodic theory, this occupation time over T goes into the probability of the ensemble to be in that particular state. That's the idea of ergodicity. You just replace these occupation fractions with probabilities. But in our case, this will be wrong. So what are the time average? You have some observable, which has a value at point x, and you multiply it by this occupation fraction. This is the time average. And again, if this goes to a delta function around the ensemble average, then you're happy you can replace this with the ensemble average. And for example, we can look at the time average position of the particle that is doing this random walk in this type of trapping model. It could depend on X, yes, it could depend on X. But for these examples, I'm going to say Qx is equal half. So you are in a simplest case in a wall, but you can do it in our papers, it's anything you want. Now, and by the way, these are simulations that I performed with a couple of Pomomaneville maps. But I just explain it in a stochastic way. But it doesn't matter, it's the same thing. So you start somewhere, and then this is the cell number. I have here 9 cells, and then you jump, and then you have these waiting times, and because you have these power laws, you see very large and different scales of power law waiting times. Here alpha is equal half. Then I can look at how long did I stay in each one of these cells. And this is the picture. If I tune alpha to be bigger than 1, which means that the average time is finite, then each cell occupies exactly the same amount. Here there are small fluctuations because it's a simple simulation. But if I go to alpha less than half, I'll see a totally different behavior. In cell number -2, for example, I had a lot of occupation time. If I take the same trajectory and make it double the time, it might be here, it might be here. All the cells in this example are identical. So obviously, you have random occupation fractions. Now, if we think a bit about these dynamics, then there is what we call population dynamics in step number. And that is, what is the probability to find a particle at x after the n+1 step? The point that n+1 step doesn't translate immediately into time. But this is super simple because it is simply the probability to jump from the right point to with qx +1 or the opposite. Either you jump from the left or right. So this is a very simple master equation. And if none of these qx's are equal 1 and you are in the usual situation, then when n, the number of jumps is big, you just look at the stationary solution. And the stationary solution, well, it's some stationary solution. For example, if I had a detailed balance, it would be a canonical ensemble. But in this sense, you have total ergodicity if you just were able to count the number of jumps. And that's why the word weak is very suitable. It's weak because in number of jumps, everything is as usual, ergodic, everything is well behaved. But the problem begins is that the time between the jumps is totally random, and it's not translating, the number of jumps is not translating immediately into time, which means that the law of large numbers is not valid. Usually the average, the number of jumps is t over the average. That's the law of large numbers, but now it's not valid because the average time is not there. There's no such thing. So the idea is, at least in my case, many times related to Levy statistics. Levy is, of course, a generalization of the central limit theorem. So let nx be the number of times the particle visits x, then when the number of jumps is big, so when time is big, the number of jumps is big but random, then the ratio nx over n goes to the equilibrium probability. But again, this does not translate into time. That's the only difference. What is the time you spend in state x? It's sum of some IID random variables whose mean is infinite, and the number of summons is n of x. So, and then you visit many times in this cell, and then you can say, okay, the distribution, the PDF of the total time you spend in some state x is given by this Levy stable law. It has index alpha. This is expected because this is the power law tail of the waiting time that I put into this model, and it has some width which is related to nx. I'm not going into the full details. Now, I have this distribution of times in one of the states. Now there is some exercise where you look at the occupation fraction, and this is tx over all the other times. There are more details. I'm not going into the details. You can do this for fixed time or different types of ensembles. But this is essentially, this is what we solve. And then we are able to prove the following. We are able to show what is the multi-distribution of these px's. And then, because we know the distribution of these guys and the observables times px, this is just a linear transformation when you need to sum over everything. of all the states in the system, then we can have a general formula for the distribution of the time average. And this formula will quantify how big the fluctuations are and say more precisely what are the fluctuations. So the idea is you have a distribution of the time average, and it is given by this not so nice formula. In it you have, because we are dealing with weak ergodicity breaking, we have the population probability. So it's not that the time average are not related to the occupation probability. They still are because of this weakness of the ergodicity breaking. They appear up here and here, and of course alpha also appears. So when alpha, for example, goes to 1, then the average sojourn time is finite. Then you expect to go to usual ergodic behavior. And then you see this alpha minus 1. This will be something to the power 0. The sum will be 1. Then you'll have 1 over this guy will be essentially a delta function, a representation of a delta function, and then the PDF of this time averages is just going to a delta function around, and that is ergodicity. When alpha goes to 1, you get ergodicity as you expect. When alpha goes to 0, you get what I call localization, and that just means that you have such long power waiting times that you just stay somewhere for a whole measurement time. Where do you stay is totally random. So there's a small problem with, not problem, but small subtlety of how you take the limit of long time. But essentially it means you stay somewhere and then you have these delta functions over all. The observables have some value at each state x, and then the time average will be equal to that, and you have some weights. So for example, the simplest example is, let's say you have this random walk in this finite system, from that wall to this wall, and the probabilities of jumping left or right are the same, half. So this is a particle in a box doing this type of dynamics. And then what you see, this line is the ergodic behavior, because on average you are in the middle of the box. So this is the delta function. This is the distribution of the time average when I normalize it by the size of the box. Very sharp, as usual in ergodic theory. Then when alpha goes to 0, it will be uniform, because all sites are equally probable and you kind of stuck somewhere. And in between, when I change alpha, I get all kinds of behaviors. So I go from very nearly strongly non-ergodic to ergodic by changing this parameter alpha. And this, we have worked with this type of questions for many systems. For example, for blinking quantum dots, you have only 2 states. You can apply this to experiment. The distribution of the time average is very flat and boring. I'm not showing it to you, but if you're interested, we can show later. 1 over F noise. Deterministic models, which I described briefly, these are the so-called Pommer-Maneville maps, where you have 0 Lyapunov exponent. Disordered systems and distribution of transport coefficients. There are many models, and on Friday I'll discuss one extension of this, which is called the infinite ergodic theory, but this will be on Friday. I will now go back to the time averages of single diffusion processes. So if you take the same model and now look at the time average MSD, the motivation is, of course, these experiments in the cell, like the messenger RNA. You just let your particle on your computer move, and you have these long trapping times, and you calculate in 1 dimension, you calculate the displacement squared, and you time average them, divide by t. Then each trajectory gives you a different slope, but the slopes are more or less parallel to one another. This is the average over many. This looks to the eye similar to what was in the experiments. We were very happy, but soon you'll see there are some problems. So let us analyze this. So again, you have a random walk with these long power law tail distributed times. This is in 2 dimensions. The size of the circle says here the guy stayed long, here the guy stayed short. It's a very simple random walk, actually, but with this power law waiting time distribution. And then along this path, you can calculate the time average MSD, which was, this is what is done in the experiments, and then compare it and see if this works. So the average, so this is a trajectory. This is x as a function of t, and you see these long waiting times. This is a typical trajectory. Alpha is 0.75. So as I said before, this, if you do the ensemble average, it gives you the mean square displacement going like t to the power alpha. This was known for 40 or 50 years already. So again, the general motivation is, you have Einstein, he said diffusion constant is MSD over time, average time between jumps. Boltzmann-Gibbs says, usual ergodic t has to be much larger than this time, tau here. We know that in disordered systems, many cases this diverges, so d goes to 0. This means subdiffusion. And Bouchot is saying, if tau goes to infinity, with that, in addition to that, you expect weak ergodicity breaking under certain conditions. So, okay, so we can look at this more carefully, and this looked like this, but there was one problem that compared to the experiment, this MSD actually increases linearly with delta, while the experiments showed something slightly different. So let us discuss this. So if you do the calculation, then the time average MSD, when you average over many trajectories, is linear in delta, but the surprising or slightly surprising effect is that it depends on the total measurement time. That means that the subdiffusion, t to the power alpha, that you find in the ensemble average, when you translate it to the time average, is totally different, because it looks normal with respect to delta, which was the lag time, but it depends on how long you measure. Why does this is called aging effect. Why does it happen? It's simple. You start somewhere, and then you experience one trap, you stay there, and then you experience a deeper trap, and you stay there longer, and then you find another trap. You stay there even longer and longer and longer. So the longer you measure, the total measurement time, you experience deeper and deeper traps. And that's why how long you measure influences your So when t goes to infinity, the measurement time goes to infinity, you go to 0, actually. You can hand-wavingly say that, the time of MHD in normal diffusion is 2d times delta. Then, okay, d is a diffusion constant, but now it depends on time. If I take the derivative of the ensemble average, I get alpha minus 1, and this is what is written here. So this is a very simple prediction, aging, that the time average MSD depends on the measurement time when you do it one trajectory after the other. We will soon show that this is found in several experiments, but before that, because the time average is a random variable, as I said already, let us look at this a little bit more carefully. So let us look at the displacement. So here I have the position of the random walker at time t plus delta minus t to the power 2. Again, this quantity I'm going to time average later. This is the increments along the trajectory. And what happens? It looks something like this. You have this effect and then nothing, this effect and this nothing. What are these guys? These are simply the trapping times. So if the particle is in one trap, this distance is going to be, it didn't jump, this distance is going to be 0, then you have 0, and then you have some activity, etc. So these times when this is 0 is exactly when you are trapped in one of these long traps, okay? What does this mean? It means that essentially when you look at the distribution of the time average, it is proportional to how many jumps you made. So in its time interval t, you have some random number of jumps. I called it S. So the time average MSD without averaging is proportional to S divided by t. This t is the measurement time, because when you divide by the total measurement time, you always get this t. So usually, so now from this proportionality to S, I can say the following, that I can define a measure of non-ergodicity in this type of experiments. That is, I look at the time average MSD divided by the time average MSD averaged over many. So this psi has, first of all, no dimensions, and if it has a distribution, it means that you are non-ergodic. In ergodic case, it will go to a delta function. And the claim is that this ratio is proportional to S, the number of jumps in the interval, over the average number of jumps. And we know how to calculate the distribution of the number of jumps, and that's why we can quantify how big are the non-ergodicity in this system. And this is given by a central limit theorem by Levy. This is the one-sided Levy distribution. For this variable, it's something called the Mittag-Leffler distribution, or the inverse Levy, because the random variable psi appears downstairs here. And it looks the following. So this is the distribution of the time average MSDs when they are normalized. When alpha is equal half, it looks like half a Gaussian. When alpha goes to 0.75, it goes something like this. And why does it approach this type of behavior? When alpha will go to 1, you'll have a delta function on the mean. So what you see here that there are some very sluggish dynamics that, you know, the peak is not at all where you expect it from ergodicity, which would be here. This is pretty wide. So we can quantify the time averages, but again, the experiment showed something different. The experiment showed that the time average MSD does not grow like delta, but it grows like delta to some power alpha. And what we believe is happening is that up to now I was discussing just an open system, a system with no boundaries. So the particle is just diffusing, but in the experiment, the particle hits the wall many times. And this introduced another time scale. How long does it take the particle to see the walls? So you can do the following. This is very general. The time average MSD you can express as the, if you average, that's the mean square displacement plus the mean square displacement plus the correlation function between two positions. That's just opening a square. And in here hides all the physics because, and this is again in the spirit of Bouchot, what Bouchot is saying that usually in statistical physics, the time averages will be only, you know, time translation invariant. But here what you have is the effect of aging, that is this correlation function has a strong correlation and it depends on the ratio of times. And you can do that in a kind of box if you want. And then you can calculate this type of correlation function. This is some beta function. My point here is not to show you that I can calculate some correlation function, it's just to emphasize that everything behind here is the fact that the correlation functions are non-stationary and they depend on the ratio of the times. And this is called aging correlation function. And again, this is found in glassy systems for many years. This is well known. And this was the starting point of Bouchot, that in macroscopical measurements, you measure such non-stationary correlation function. And from here, it's obvious that you have ergodicity breaking, I would say, but of very special type because of this ratio of these two times. And then when you do this and you look at not delta, which is long compared to the time you hit the wall, you get this anomalous behavior. Not like before, but still you have aging. And this is more what we believe is more related to the experiment because in the messenger RNA experiment, you hit the wall many times, so you had a third time scale. So unfortunately here, what we see is some slight complexity. You have the delta, the time difference, you have the measurement time, and you have the time to transverse the system. So you have 3 times. The measurement time has to be bigger than delta, of course. But then depending on the other time scale, you can have different dynamics. This is shown, soon I'll show you this example. But here you see one experiment where you see this aging effect. So this is the time average mean square displacement. This is on the cell membrane, you have some ion channel and it is diffusing around, and Diego Krpaf was able to follow it. And then you measure the time average MSD, but usually you are used to the fact that you change the lag time, the time difference, which I called delta before. Now he's changing simply the measurement time. And you see that when you increase the measurement time, this is for fixed lag times, milliseconds, or roughly seconds. Then you increase measurement time. The older you are, the slower you move. All of us know this, right? I mean, as you are becoming older and older, you're more trapped wherever you are and you don't move, and then your diffusion constant goes down. This is found already on the microscopical scale of a single ion channel in the cell, but obviously this is non-stationary, and this is a signature of weak ergodicity breaking, this aging. Usual behavior would be simply a straight line. You can make the analysis a bit deeper by simply measuring the waiting time PDF, and you see and you can relate between this exponent, which is here, I have to admit, very close to 1. You can relate between this and the non-ergodic dynamics. And we have a review in physics today on this issue, if you're interested in more details. And here I'm showing you another experiment in the cell. This is in a virus, where you follow one tag particle, and you see that for short times you have linear in delta, which is like an infinite system, which I showed you at the beginning, and then you go to some time when you hit the walls to some anomalous behavior. So there is a lot of experimental activity. Another example of an experiment was these 3 experiments. I'm just showing you one. When they measure, for example, receptor motion in living cells. Actually, this experiment is this experiment. And the bottom line is that the mean square displacement depends on 2 times, on this delta, the lag time, and on measurement time, t. And you see, the longer you measure, the diffusion goes down. You are non-stationary, obviously, and obviously non-ergodic. And this was the prediction that we made, that, you know, it will go down. So some rare occasions, my theory actually work in experiment, but, or part of the predictions work. How much time do I have? 10 minutes, thank you. So now I want to go in a slightly more microscopical model, and this is called the quenched trap model, which is maybe 50 years old. And again, people used it for electrons, the diffusing in disordered systems when they treated them as classical objects. And the idea is, let us define a random potential, a random energy landscape as a function of x. And at each point x, we have a trap. We assume no barriers here. And the depth of the trap is called EI, energy. But you assume that the distribution of the depth of the energies is exponential with some scale, which I call Tg. Tg is the glass, kind of glass temperature. So it's a measure of the disorder. But again, the assumptions on the energy fluctuations are, you know, the fluctuations of energy are not big. These are exponential. What is also assumed in this model is that when you start here, you can jump, let's say, to the right or left with equal probability, but the waiting time is, first of all, exponential here, but it will be described by activation, very simple activation. And that means the waiting time depends on Ex over k Boltzmann T. There is some prefactor here, which I take to be equal 1. So in principle, if you return many times back to this trap, it will be exponential kinetics. But you have different energy traps. And from this distribution of energies, you can very easily show that the waiting time PDF, when you average over everything, is tau to the 1 plus T over Tg. Again, Tg is a measure of disorder, and T is the usual thermal temperature. So here you have an example where I can change, for example, temperature, and then I change alpha. And when the temperature is less than the Tg, then you will have all kinds of anomalies. This is, again, well known. And when T is greater than Tg, more or less, you are in a normal phase. So you have this transition. And the reason, the deep reason is very simple, is that this waiting time, this Arrhenius law, you see this exponential to the power E, a small change in energy, which is this, you know, small fluctuations here, is enough to induce a very big fluctuations in the waiting time. So this is an exponential conspiration. Because of this exponential small changes in energy and exponential density of states, you get very broad waiting times, and this is all anomalous by a simple trick. This distribution is this exponential. So you have random energies, and the average size is Tg, but these distributions are exponential. Yeah, but Poisson, it's not a Poisson process. But again, by doing this transformation from exponential, the time it takes is proportional to E over temperature, and then because of small fluctuation of energy, gives you these power law waiting times when you average. So now you have to imagine the system, let's say, on a ring. And you do dynamics, and let's say you measure the mean square displacement. If you have a ring and you have one realization of disorder, eventually this system will become ergodic, because you have finite amount of energy traps, and for one realization of disorder, you have some minimum of the energy, something which is random, and for that system, you will have some equilibrium, and it will be totally ergodic. So here we come to something maybe I think should be discussed here, is the difference between ergodicity breaking and non-self-averaging. In experiment, this could be very difficult to distinguish between the two, which means that you can do a time average, let's say time average MSD on one of these realizations of energies, and then you can repeat it on another realization, and these will not give you the same. Or you can have a specific realization of disorder. You do a time average, then you go to the same exactly specific one. You do a time average. The time averages will, if you do one realization, will converge to something. It will be ergodic, but then you go from one sample to the other, it will be different. When there is a, that is, the Hamiltonian is random itself, and then you have this property of non-self-averaging, which looks like non-ergodicity. So how do we quantify the fluctuations? We need to look at different systems, and you measure something, and then one system gives you one answer when you look at the time average or an ensemble average, and then another system gives you some other thing because you are working in a disordered environment. And then we can ask, this model is very similar to the continuous time random walk in the mean field sense, but which one of these quenched disorder, or we call the continuous time random walk is called annealed disorder, which one will be, where will the fluctuations be bigger? And also here there is the role of the initial conditions. That is what I described before. You have this random energy surface, you throw a particle inside, you start your random walk. But you can also think about the following. You have this random energy landscape, you throw the particle inside, you equilibrate, and then you start your observation. All these things, which people don't really care too much about, are super important. We discussed them more recently in 2016. And I'll just give you the results for this quenched trap model. So the time average MSD, when you time average and then you average over disorder, over many realizations of disorder, it is again linear in delta, even though then in an open system this will give you subdiffusion. It's linear in delta. This is simply because when delta is small, you linearize the increments. And it depends on the size of the system in this fashion. So what is happening here? Instead of aging, dependence on time, you have dependence on the size of the system. But this is only when you sample the system many times, like let's say on a ring. And why does it depend on the size of the system? You have these traps, and then the longer the system is, the deeper you can find the trap. So you have big system, some trap, bigger system, even deeper trap, etc., etc. So what you see here is that again, all these averaging procedures, which usually are all the same, are very different because previously I had here the total measurement time. If I look at one realization of disorder, this is ergodic, so I can look at the mean square displacement averaged over equilibrium initial conditions. It's also important. This is just given by Einstein formula. This is the measurement time, sum of all the waiting times in your traps, divided by L. You have L traps. What is this? This is simply the average time between jump. This is just what Einstein told us. But the point here is that this guy will vary from one realization of disorder to the other. Usually you say, oh, sum of tau I divided by L, this will give you some number. This will be the same in every system. No, here it's different because this guy is random even when L is large. And that means that these time averages, they are random because the energy landscape is random. Now we can define these type of fluctuations around ergodicity in the following way. This is SA because I worked with Saito and Akimoto. We call it SA, but it's self-averaging parameter. And that means you take the time average, you square it, and then you average on distributions of disorder, realizations of disorder. You don't do it for one realization, you do it for many, and you average it. Then I can look at the same, but here I have the square, and here I have the average, and then the square, so this is the variance, and I normalize it over disorder. And I'm looking at the observables which are not zero because I'm looking at MSDs, etc. On the other hand, I can look on the ergodicity breaking parameter, I call it EB, which is, you do the same, but now I do it in the annealed version of the model. I have a time average, and then I average over many trajectories. This is a measure of ergodicity breaking, but again, they are very similar, maybe impossible even to distinguish in real experiments. And then I can plot them for the two models. So I have here a model. This is the new model in the quenched disorder, and this is the old model where I plot the ergodicity breaking parameter when I have this assumption of renewals. And what you see here is that the self-averaging parameter is much bigger when I go down in alpha than the anneal one. Why is it much bigger? Because here there are two effects. First of all, you have the waiting times, but also we equilibrate the system at the beginning. So what we do, we have a system, we let it reach equilibrium, so you start in a very deep trap. And this starting time makes the fluctuations even bigger, because some guys are really stuck and don't move. And that's why when you go to smaller alphas, you have this type of divergence. So there is a difference between the anneal and the quenched disorder. They are not the same. We looked at distribution of diffusion constant. Again, in one system, you have a diffusion constant. And that, again, related to Levy statistics, this should be compared to what I had before. That was more in this regime. It was more like a peak. So again, in the quenched disorder, things just become worse. The fluctuations are much bigger, wider, and variability of diffusion constant is enormous. So let me stop here. I just wanted to say that, some brief, usually Boltzmann-Gibbs systems, usual thermal systems, they have also chaos, and they usually exhibit normal diffusion. Weak ergodicity breaking is found for certain types of non-stationary processes that exhibit this anomalous diffusion, where T goes to the power alpha. This means divergence of some microscopical scale. There is a central limit theorem, which you saw several times. This is the Levy central limit theorem here. It's the Gaussian central limit theorem. If you read the old book of Hinshin that shows how normal Boltzmann-Gibbs is related to Gaussian central limit theorem, etc. Here you have a time average MSD, time average observables go to a delta function. Here you have a more general formula that still is related to the equilibrium properties. I did not discuss, but in the context of chaos, then this is related to chaos, this line. But in the context of Pomoma-Neville maps, I mentioned briefly, you have lambda equals 0, and then you have infinite invariant densities, which will be discussed in next Friday in my second talk. Okay, I would like to thank you. Just mention some popular articles I have here, if you are interested. Yes. So